Well, I would like to speak of the dynamics of neural assemblies, and in particular about chaos in such system. Can I get the next slide, please? Well, so let me describe briefly simplified version of neural assembly. Each neuron, which I count from 1 to n, has a potential which I normalize to the interval 0, 1, and it increases in the average. It will go up and down, but when it reaches the value 1, there is a so-called spike which is created, and the potential jumps back to 0, where it remains for a latency time of 2 or 3 milliseconds. And then its time evolution is given by something like the leaky integrate and fire equation, which is on the next slide. Yes, this gives the derivative of the potential as a negative term, which is exponentially decreasing. And then there's input by excitatory neurons and input by the inhibitory neurons, and also an external time-dependent forcing. Now, the G of VI minus VE is something that depends on the spike of the other neurons and which acts for a limited time. And the external forcing is essential in this time evolution. I'm not considering a system of neurons alone, but a system of neurons which are driven by some external perceptions, and then will probably react and cause some action. Okay, so the important thing is that I do not consider that there is learning in this system. Learning is ignored, and I consider the time evolution in the absence of learning. So can I get the next slide? Okay, so the system is described by the VIs corresponding to the various neurons, and which are between 0 and 1, and then a collection of discrete sets which correspond to the firing times of the various neurons. And these collections have mutual distances greater than the latency time. So there is a time evolution of these axes, and I assume that there is some initial distribution which is independent, which is continuous, which has continuous density. And then I look at the the asymptotic behavior in time. So for simplicity, I assume that the external action is periodic in time and of period, say, t, which is greater than the latency time. So there will be a time evolution from the interval 0t to the interval 0t plus n times the constant t. Now, if there is an initial distribution of the axis which has continuous density, then we can assume that there is some asymptotic distribution which is part of a discrete set. So in general, the distribution of systems, of dynamical systems, these ergodic distributions can be part of an extremely large set. However, saying that the initial distribution has density with respect to Lebesgue, has continuous density, has the effect that the asymptotic distributions are part of a set which is countable. So it can be either empty or finite or infinite, but countable. And if we have some kind of mixing for the system, which we can assume for nervous assemblies, probably there will be just one asymptotic distribution. So I can, in fact, ignore the collection of firing times and consider the time evolution for only the potentials Vi, because the potentials Vi in one interval 0t will determine the potentials at later times, and therefore we can ignore them in the study from 0t to 0t plus t. So I'll assume that I have a measure, a probability measure on the distribution, on the family of potentials. This probability measure will in general be singular with respect to the Lebesgue measure, but that's not important. What is important, can I have the next slide, please, is that it may be chaotic. Chaotic means, let me not go to the details of the formulas, means that if there is a small change in initial condition, this change will grow exponentially, at least when it remains small. And the rate the largest rate of growth is called the largest Lyapunov exponent, and we assume that the system is chaotic if this largest Lyapunov exponent is strictly positive. May I have the next slide, please? Okay, so the standard situation of time evolution is a diffeomorphism of a compact manifold, and we consider a family of distributions, of probability distributions on this unstable manifold, which are such that there is a density on unstable manifolds. So unstable manifolds are the manifolds of points which grow exponentially with time. Now, if we have an initial condition which has density with respect to the bag, then there will be also a density of the asymptotic manifold on these unstable manifold. And one calls SRB the measures which have a density on unstable manifolds. And as I have mentioned, the SRB measures form a discrete set, which may be infinite, but which we shall take to be just one set. And these SRB measures are the natural measures that describe chaotic system. The next slide, please. Okay, we have a reasonable understanding of the statistical properties of neural systems if these systems are chaotic, namely if the largest Lyapunov exponent is positive. The problem is that if we look at a given time evolution, like the one that I've sketched at the beginning of the talk, it's very rarely possible to prove that we have chaos. However, numerical studies indicate that chaos is frequent if the time evolution is nonlinear, if we have high dimension, and if we are away from periodic attractors. So it is reasonable to assume that for neural assemblies, there will be a chaotic time evolution. Now, this should be independent of the details of the nervous connection. In fact, we cannot, can I have the next slide, please? Next slide, please. Yes, genetically, the neural architecture is determined, but not the details of neural connection. So proving that there is chaos in neural systems is very difficult to check, because there's no information on the details of the neural connection. I've tried, from the general information that we have on neural systems to prove chaoticity, but that's not, I've not been able to do that. So one must simply assume that probably neural systems are chaotic. This is in agreement with the fact that destroying one neuron does not change the general structure, and therefore is in agreement with the chaoticity. And therefore, I can, let's go to the next slide. Okay, I have here given a general reference to SRB measures, and the fact that neural systems are probably chaotic and described by SRB measures conforms with a certain number of features of these systems. So looking at the nervous system will give an impression of randomness. Nevertheless, these systems are probably deterministic but chaotic, and the fact that there is apparent randomness does not prevent information from being transmitted by these nervous systems and giving rise to appropriate responses to inputs. So I will stop there. Thank you.